Limiting reactant and percent yield. So limiting reactant, when we mix substance A with substance B to produce some products, we want to figure out how much of substance A and how much of substance B is needed to produce a certain quantity of the product. So if we know that we want 5 grams of the product, well, we would have to add a certain mass of substance A plus a certain mass of substance B in order to produce those 5 grams of the product that we want. And we can do these calculations and figure this out. Now, we typically don't want to waste substances. So we want to know how much exactly of each one of the reactants we would need in order to produce the desired product. So in here, it says determine the number of those molecules that can be made given these quantities of reactants. So if we go through here, we need 2 of these plus 1 of these to give us 1 of those. So let's start crossing these out. 2 of those, 1 of those gives us 1 of those. 2 of those, 1 of those gives us 1 of those. 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1. And we ran out of the little blue balls, but we still have these left over. We have created all of the product that we possibly can because we don't have any more of these to add. So if we assume that these are hydrogens and these are oxygens and that's water, in this example we ran out of hydrogen, so we can't make any more water. We still have oxygen left over, but regardless, we can't make any more water because we ran out of hydrogen. This is what our limiting reactant is. The limiting reactant is the reactant that limits how much product we can make. So in this example, the hydrogen is our limiting reactant, and we have excess oxygen. The limiting reactant is the substance that we run out of in the reaction. If we added 4 more hydrogen, then we could produce 2 more water molecules because we have excess oxygen in order to be able to do that. So the limiting reactant, again, is the reactant that limits the amount of product that can be made. The reaction stops when the limiting reactant is used up. The excess reactant is the reactant that remains when the reaction stops. There is always leftover excess reactant. What was the excess in that reaction? The larger blue ball. So in the example I gave, that would have been the oxygen. So what is the limiting reactant here? So each bike needs 2 wheels, a frame, and a pedal assembly. 2 wheels, a frame, and a pedal assembly. 2 wheels, a frame, and a pedal assembly. And then we have excess wheels and excess frames. Sorry, 1 excess frame. But we ran out of the pedal assembly. We can't possibly make another bike without the pedal assembly. So the limiting reactant in this example is the pedal assembly. So how do we figure out what the limiting reactant is? First, convert reactant 1 to moles or mass of the product. Then convert reactant 2 to moles or mass of the product. Compare the answers. The smaller answer is the maximum theoretical yield. So calculate the number of moles of water that can be made by the reaction of 1.51 moles of H2 with 9.32 moles of O2. So first you're going to calculate the theoretical yield of water assuming H2 is the limiting reactant and that O2 is the excess. Then you're going to calculate the theoretical yield of H2O assuming that O2 is the limiting reactant and that H2 is excess. So we start with 1.51 moles of hydrogen and 0.932 moles of oxygen, and we're trying to figure out which one is going to produce the least amount of moles of H2O. So we're going to go this one to moles of H2O, this one to moles of H2O, and compare. Whichever produces the lower amount of H2O is the limiting reactant. Why is it the lower number? In this example, even though we have 4 frames and 4 sets of wheels, we still can't produce 4 bikes. So if we were to say, how many bikes can we produce based on the number of frames? Well, we can produce 4 bikes based on the number of frames. How many bikes can we produce based on the number of wheels? Well, we can produce 4 bikes based on the number of wheels. But how many bikes can we produce based on the number of pedal assemblies? We can only produce 3 because we only have 3 pedal assemblies. So in order to produce full bikes, the most bikes we can produce is the one with the least number of ingredients. The lowest number is going to be what we can theoretically produce. So same thing with this. We convert moles of this to the product, moles of this to the product. Whichever one produces the least amount, that's the amount that is our theoretical yield. So doing this example, 1.51 moles of H2, we have moles of H2 on the bottom, we're converting to moles of H2O. These coefficients come directly from our equation, so there's a 2 in front of the H2, there's a 2 in front of the H2O. So when we multiply, divide, we get the same 1.51 moles. If we do the same thing for 0.932 moles of oxygen and convert that to the product, moles of oxygen is on the top, so moles goes on the bottom. We're converting 2 moles of H2O, and where do these numbers come from? The coefficients. So we have an imaginary number 1 in front of the O2 and 2 in front of H2O. So 1 in front of O2, 2 in front of H2O. Multiply across the top, divide away the bottom, we get 1.86 moles. Now we compare. Which one of these produced the smaller number? 1.51. So the theoretical yield, or the maximum yield of water, is the lower of the two numbers. Even though we can produce 4 bikes with the 4 frames, we can't because we only have 3 pedal assemblies. Even though we can produce 1.86 moles with 0.932 moles of oxygen, we can't because we end up running out of hydrogen. So we can only produce 1.51 moles of H2O. This is our maximum theoretical yield. How much H2 and O2 remain when the reaction stops? Well, H2 is the limiting reactant. Nothing remains. So if it was used up in the reaction, it's done. O2, though, is excess. And we can calculate the amount of oxygen used in the reaction with H2 and then subtract that from the original amount. So if we convert H2 to O2, we can calculate how much moles would be used in this reaction. 0.932 moles to start, and we have 0.755 moles that's actually used in the reaction. So it equals 0.177 moles of excess O2. Okay. So these problems are written out for you, so I will just kind of follow along with what's here. Calculate the mass of copper, question mark, grams. That can be made from a combination of 15 grams of aluminum with 25 grams of copper 2 sulfate. So first, we're going to take 15 grams of aluminum to the product, grams of the product. Then we're going to take 25 grams of copper 2 sulfate to the product. Then we're going to compare. The smaller number is the correct answer. So looking at this one, if we start with 15 grams of aluminum, we do grams of aluminum to moles of aluminum to moles of copper to grams of copper. So following what we learned previously and going through the correct series of steps, 1 mole is equal to the calculated mass from the periodic table. And then we use the mole to mole ratio. There's a number 3 in front of copper and a number 2 in front of aluminum. And then here we use our 1 mole is equal to the mass from the periodic table. We're going to multiply across the top, divide away the bottom, and we end up with 53 grams of copper. Here, we're starting with 25 grams of copper sulfate, copper 2 sulfate. So again, we did this one, now we're doing this one. So we do copper 2 sulfate to moles of copper 2 sulfate, moles of copper 2 sulfate to moles of copper, which is our new substance, and then from moles of copper to grams of copper. We're going to fill in our conversion factors. 1 mole is equal to the mass from the periodic table. Here is our mole to mole ratio because we're converting between different substances. There's a number 3 in front of copper and a number 3 in front of copper 2 sulfate. Then we use the 1 mole is equal to the mass from the periodic table. Multiply across the top, divide away the bottom, and then we get 9.96. So copper 2 sulfate is the limiting reagent or limiting reactant. Reagent and reactant can be used interchangeably. The theoretical yield, or the possible total amount that we could produce of copper, is 9.96 grams. So this is our limiting reactant, which produced our theoretical yield of 9.96. On the test, you're going to be asked, what is the limiting reactant? What is the theoretical yield? Okay, so try to work through this one. Pause the video and go ahead and work through it, and then we'll unpause and go through it together. Okay, so what is the limiting reactant when 3 moles of copper are reacted with 3 moles of silver nitrate in the following equation? Now we have 2 products to choose from. The problem doesn't specify which product we're supposed to choose. It doesn't matter which product we choose. We can choose either one of them. I'm going to choose to go to silver. So 3 moles copper, moles of copper, 2 moles of silver, and I'm going to use the coefficients that are found here because we're right into our mole to mole ratio. So 1 mole of copper for every 2 moles of silver, and we get 6 moles of silver. Now if I do 3 moles of silver nitrate, moles of silver nitrate, we have to make sure we're converting to the same substance. So we can't convert one to one and the other one to the other one. We have to convert to the same substance. So that's why we're taking both of these to moles of silver. Now the coefficients in front of these are 2 and 2. So we end up with 2 moles of silver. So the maximum theoretical yield that we can make is 2 moles of silver, but it's asking which one of the reactants is our limiting reactant. So which one produced the smaller number? Our silver nitrate. If you did it in the other direction, in the other way, it works as well. So let's try it in the other way. So again, we have 3 moles, 3 mole, and now I'm going to convert both of them to this one. 3 moles of copper, to moles copper to nitrate. This is our mole to mole ratio. We're going to use coefficients. This is 1 to 1, and that equals 3 moles of copper to nitrate. So we do the other one, 3 moles of AgNO3, moles of AgNO3, 2 moles of copper to nitrate. And we use our ratios. So it's 1 and 2, multiply across the top, divide away the bottom, equals 1.5 moles. This is our theoretical yield of copper to nitrate, and this is still our limiting reactant. So no matter which product you convert this to, it's going to give us the same answer. You just have to make sure that both of the reactants go to the same product. What is the mass of silver produced by the reaction of 3 moles of copper with 3 moles of silver nitrate? Go ahead and pause and try to calculate this. Okay, so we have 3 moles of copper with 3 moles of silver nitrate, and it's asking for the mass of silver. So we're going to convert both of these to silver. So we're going to start with 3 moles of copper. Moles of copper, we can go directly to moles of silver. And then they want the mass of silver. So moles of silver, 2 grams of silver. Now we fill in our conversions. So this is our mole to mole ratio. We're going to use coefficients. There's a number 2 in front of silver and a number 1 in front of copper. And here, since it's the same substance, 1 mole is equal to the mass from the periodic table, 107.87 grams. We're going to multiply across the top, divide away the bottom. 3 times 2 times 107.87. We can ignore the ones, and we get 647.22 grams. Now we're going to do the 3 moles of silver nitrate. Moles of silver nitrate, we can go directly to moles of the new substance, which is moles of Ag. And then for moles of Ag, moles of silver, we can go to grams of silver. Here's our mole to mole ratio. There is a number 2 in front of silver and a number 2 in front of silver nitrate. And here we're going to use 1 mole is equal to the mass from the periodic table, 107.87 grams. We're going to multiply across the top, divide away the bottom. We get 323.61. That is the lower of the two numbers. That is our final answer. So how to calculate excess? Convert the two reactants to one of the products in order to find the limiting reactant. Use the mass of the limiting reactant to find out how much of excess can be produced. Subtract the mass that was produced from what you initially had from the mass that can be produced, using up all the limiting reactant. The difference is your excess. So, find the limiting reactant and calculate the mass of the excess. Consider the following reaction. Assuming we start with 30 grams of ammonium nitrate and 50 grams of sodium phosphate. What is the limiting reagent? What's the maximum amount of each product that can be formed? How much of the other reagent is left over after the reaction is complete? Now they want the maximum amount of each product. So first, we're going to convert both of these to that, the mass of this one. Then we're going to convert both of these to the mass of this one. And I don't have much room on here, so I'm going to rewrite this on a new slide and then go through it from there. Copy that. All right, I have a little more space now. So we have 30 grams of this and 50 grams of this. I'll get rid of this to give us even more room. All right, so I'm going to take 30 grams and 50 grams to each one of these products. "30 grams of NH4NO3 So grams of NH4NO3, we put grams of that on the bottom. So then we're converting to moles because we have to get to that mole to mole ratio. From moles, we can go to moles of the new substance. So first we're going to tackle the ammonium phosphate. And then from moles, we want to get to grams. Okay, so 1 mole is equal to the calculated mass from the periodic table. So we have 1 nitrogen, we have 4 hydrogen, we have another nitrogen, so we're going to turn this into 2 nitrogen. And then we have 3 oxygen. So NH4NO3, I'm going to get the actual masses. So I'm going to pull out a periodic table here. Nitrogen is 14.007, and there's 2 of those. So we have 28.014. Hydrogen is 1.008, and there's 4 of those. So we have 4.032. And oxygen is 15.999, and there's 3 of those. So we have 47.997. So the total mass is going to be 032 plus 28.014, 80.043 grams. So 1 mole is equal to the mass from the periodic table. Now we're going to use our mole to mole ratios. So NH4NO3 has a number 3 in front of it. And then we're going to put a 1 and a 1 here. NH4,3PO4 has a 1. And then here we do the mass is equal to, or 1 mole is equal to the calculated mass from the periodic table. So on this side, we have 3 nitrogen, plus we have 3 times 4 gives us 12 hydrogen, plus we have 1 phosphorus, plus we have 4 oxygen. And we're going to add this up to get the mass of that guy. So we have 3 times 14.007, and that's going to give us 42.021. We have 12 times 1.008, and that's 12.096. Then we have 1 phosphorus, 30.974. Then we have 4 of oxygen, which is 15.999, gives us 63.996. So the total mass here is 149.087. We're going to multiply across the top and divide away the bottom, and we can ignore the number ones. We get about 18.6 grams. Now we have to do the same thing with the other one. So we have 50 grams of Na3PO4 and we're going to do our 3 parentheses again. So we have grams of Na3PO4 to moles of Na3PO4. And we're going moles Na3PO4 to moles of our new substance, Na3PO4. NH43PO4 from moles of that new substance, NH43PO4, we're going to grams of that substance. So now here, we're going to put our 1 mole is equal to the calculated mass from the periodic table. So we have to calculate this mass. I'm going to do this off in the corner here. There's 3 sodium, 22.099 times 3. Wait, sorry, it's 990. 22.990 times 3. 68.97. We have 1 phosphorus, which is 30.974, plus we have 4 oxygen. $30.996. We're going to add these up. $163.94. Here's our mole to mole ratio where we're going to use the coefficients. There is a number 1 in front of Na3PO4. There is a number 1 in front of NH43PO4. So 1 mole is then equal to the calculated mass from the periodic table, which we calculated up here previously. So we can just put that same number here. We're going to multiply across the top and divide away the bottom, ignoring anything that's the number 1. And we get 45.5. So now we know that this is the maximum theoretical yield produced by this mass of NH4NO3. So now we know that we have excess Na3PO4. So there's a couple different ways we can do this. We can either convert from 30 grams of NH4NO3 to the limiting reactant, the excess reactant of Na3PO4, or we can convert from the product of 18.6 grams to figure out how much Na3PO4 can be produced from that. Use the mass of the limiting reactant to find out how much of the excess can be produced. So we're going to pull up a new slide here. And we're going to copy this. So now that we know that we have 18.6 grams maximum that can be produced from 30 grams of NH4NO3, we are going to convert 30 grams of NH4NO3 to however many grams of the other reactant. So we still haven't answered this question here. What is the maximum amount of each product that can be formed? Well, we know how much maximum product this can be formed. We didn't calculate this yet. It's the same exact process, except instead of using the NH43PO4, you're using the NaNO3. So I won't go over that one today. But if you do have questions, I'm happy to meet with you in tutoring and we can go over that example as a class if needed. So, moving on with the second part though, how much of the other reagent is left over after the reaction is complete? We're going to convert one reactant to the other reactant to see the limiting reactant to the excess reactant to determine this. So we have 30 grams of NH4NO3, and we're going to convert that to grams of the other reactant. So grams of NH4NO3 to moles, NH4NO3. Then from moles of that substance, we can go to moles of the new substance. And from moles of the new substance, we're going to go to grams of that substance. So 1 mole is equal to the mass from the periodic table. We calculated the mass of NH4NO3 to be 80.043 grams. Now over here, we're using the mole to mole ratio, so we're going to use the coefficients that we have in the problem. So there's a number 3 in front of NH4NO3 and a number 1 in front of Na3PO4. Here, we're using 1 mole is equal to the mass from the periodic table. So to calculate the mass of Na3PO4, it's 163.94 grams, which we calculated previously. So 16394. We're going to multiply across the top and divide away the bottom. So we have 30 times 163.94 divided by the bottom, and we end up with 20.5 of Na3PO4 can be produced by 30 grams of that limiting reactant. In the original problem, though, it said that we started with 30 grams of that guy and 50 grams of this guy. So if this is the total amount that we can produce with this reactant, but we started with 50 grams, how much left over will we have? So 50 grams minus what we just calculated will give us how much excess? $50 minus 20.5 gives us 29.5 grams excess. Okay, so there is another reaction that's very similar to what we did, and you can take the time to go through this. Again, if you have questions about this problem, I'm happy to go through it with you as a class or in individual tutoring one-on-one session. We can go through the answer to this one. To determine the efficiency of a process for making a compound, chemists compute the percent yield of the reaction. So the percent yield is the actual yield divided by the theoretical yield times 100%. The theoretical yield is what we've been calculating with the limiting reactant so far. So that's resulted using stoichiometry. That's the maximum possible amount that we could produce given those reactions in perfect conditions. The actual yield is what you actually end up with. So if I were to mix chemical A with chemical B and estimate, like, I should have 60 grams of the product by the time I'm done mixing those two together and they react completely. However, If I happen to spill something on the counter, if I happen to weigh it incorrectly, if some of the powder of the reactants sticks in the weigh boat, we may not actually get 100% yield. So there's error that can happen in the lab when you're actually producing or doing these reactions where you can lose part of the reactants. And that what happens gives you your actual yield. So when you actually perform this physically in a lab, you tend to produce less product than you would under perfect conditions, because it's near impossible to reach perfect conditions in a lab. So to find the percent yield, you're going to calculate the percent yield. You're going to calculate the theoretical yield first, and then compute the percent yield. So here's the problem, the sample problem. Calculate the percent yield of PCl3 that results from reacting 5 grams of P with excess Cl2 if only 17.2 grams of PCl3 were recovered. So this is what was recovered. This is our actual yield. So now they want to know what the theoretical yield is. So if we start with 5 grams of P, how much should we theoretically produce? Well, 5 grams of P goes on the bottom. We convert to moles, moles to moles, moles to grams. So we get 22.2 grams of PCl3. So how much should we actually produce? 17.2 grams was actually produced when we did this in the lab. But theoretically, we should have been able to produce this based on the calculation. So to figure out the percent yield, we do percent yield is actual yield divided by theoretical yield times 100%. So we only got 17.2 grams out of the 22.2 that was possible, times 100% gives us 77.5%. In a reaction to produce ammonia, the theoretical yield is 420 grams. What is the percent yield if the actual yield is 350 grams? So this is just as simple as plugging it into your calculator. 350 grams divided by 420 grams times 100% gives you, don't think the answer highlighted on this one, so let's do it in our calculator. 350 divided by 420 times 100%, 83.3%. What is the mass of silver produced by the reaction of 3 moles of copper with 3 moles of silver nitrate, assuming that there is a 67% yield? So this type of problem we aren't going to cover in this class. We don't have to actually figure out percent yield from the back end. Your percent yield questions will be as straightforward as this one, where you just plug it into the equation, or this one where you can calculate it this way. So I'm going to go ahead and delete this slide. You won't have to worry about completing this. And that brings us to the end of this lecture.